Hello guys, welcome to the one more lecture on infinite series. So in the previous lecture we learned about what is infinite series and how to find the convergence and divergence of the infinite series, and also about the Cauchy's root test and D'Alembert's ratio test. So in this lecture I'm going to discuss few examples related to the Cauchy's root test. So already we know how to apply Cauchy's root test and all. So if the function un is expressed in terms of powers of n, so then we can directly apply the Cauchy's root test here. So the formula for Cauchy's root test I'm going to discuss once again. So if summation un is a series of positive terms, limit n tends to infinity, un whole power 1 by n is equal to L. So where L should be a finite quantity, and then the series is said to be convergent if this finite quantity is less than 1, and similarly we can conclude the series is divergent if L is greater than 1, and test will be fails if L is equal to 1. So now we'll see few examples related to the Cauchy's root test. So before going to the Cauchy's root test, I'm going to give the standard limits again. The first one is limit n tends to infinity, n power 1 by n is there in the problems, we can replace it as 1. So limit n tends to infinity, 1 plus 1 by n whole power n, we can replace it as e. Limit n tends to infinity, 1 plus x by n whole power n can be replaced as e power x. So we'll discuss some examples now. The first problem, find the nature of summation n from 1 to infinity a power n square x power n where a is less than 1. So here we can observe that. So here they not mention the which test we have to apply. So by seeing the function only we have to come to know that which test we should apply here. So the function is given like in terms of powers of n is there. So if the powers of n is there means already I told that directly we can go for the Cauchy's root test. So I can take the un is equal to an square xn as the un value here. So I am taking here un is equal to an square x power n. So according to the Cauchy's root test, we have the formula like limit n tends to infinity un power 1 by n. So to get un power 1 by n, in the given un equation, I am going to take power 1 by n on both the sides. So if I apply power 1 by n on both sides of the given equation, I will get the equation like un power 1 by n is equal to a power n square whole power 1 by n x power n whole power 1 by n. So here in the an square whole power 1 by n, 1 n term by n gets cancelled. X power n whole power 1 by n also 1 n term gets cancelled. So I got the equation like a power n x. So now for this function I'm going to apply the limit n tends to infinity. So now if I apply limit n tends to infinity on both sides of the equation, so limit n tends to infinity un power 1 by n. So the Cauchy's root test formula I got it now is equal to limit n tends to infinity a power n x. Since the value of a is less than 1, and so 1 power infinity will be obviously it is 0 since the value is less than 1. So I got the value 0. So 0 will be less than 1. So we can conclude that the Cauchy's root test summation un is convergent. So since already I told that in the Cauchy's root test, if that finite quantity is less than 1, we can take it as a convergence series. So we'll see one more example related to the Cauchy's root test. Test for the convergence of summation n from 1 to infinity n plus 1 by n whole power n square into 1 by 3 power n. So here also we can observe that the function is in terms of powers of n we are having. So take the function un is equal to n plus 1 by n whole power n square into 1 by 3 whole power n. So since it is a powers of n, we can use the Cauchy's root test. So according to the Cauchy's root test, I should have un power 1 by n. So I'm going to apply un power 1 by n on both sides of the equation. So I will get the equation like un power 1 by n is equal to n plus 1 by n whole power n square whole power 1 by n into 1 by 3 power n whole power 1 by n. So on cancelling the powers and simplifying it, I will get un power 1 by n is equal to n plus 1 by n whole power n into 1 by 3. So now I can apply the Cauchy's root test for the above equation. So applying the Cauchy's root test means applying the limit n tends to infinity on both sides of the obtained equation. So I will get the equation like limit n tends to infinity un whole power 1 by n is equal to limit n tends to infinity n plus 1 by n whole power n into 1 by 3. So here I can take n common factor in this function. After applying the Cauchy's root test, I can take n common factor. So I will get the equation like 1 plus 1 by n whole power n into 1 by 3. I got it on simplifying the equation. And already we know that limit n tends to infinity 1 plus 1 by n will be e according to the standard formula, and I'm keeping 1 by 3 as it is. So the solution will be e divided by 3. On replacing the value of e, I got the value is 0.9. So 0.9 is obviously less than 1. So we can conclude that the summation un is an convergent series. So we'll see one more example related to the Cauchy's root test. Test for convergency of summation n from 1 to infinity 1 plus 1 by square root of n whole power minus n whole power 3 by 2. So here also the function will be expressed in terms of powers of n. So we can apply the Cauchy's root test here also. So take the function first. Un is equal to 1 by 1 plus 1 by root n whole power n power 3 by 2 I am taking. So since it is negative, I am shifting the function to denominator. I can write the equation like this. So applying un power 1 by n on both sides of the equation, I'll get the equation like 1 by 1 plus 1 by root n whole power root n. So on applying the whole power 1 by n for n power 3 by 2, it will be equal to root n. I will get it. So now I can apply the limit n tends to infinity on both sides of the equation to satisfy the Cauchy's root test. So limit n tends to infinity un power 1 by n is equal to limit n tends to infinity 1 plus 1 by root n whole power root n. I got it. Since limit n tends to infinity 1 plus 1 by n a whole power n will be equal to e. In the same way, on comparing the both the equations, I can write like this also. Limit n tends to infinity 1 by 1 plus 1 by square root of n whole power root n will be equal to e. Since the function is available in the denominator, I can write like it is 1 by e. So 1 by e will be equal to 0.367. It is less than 1. So I can conclude the given series summation un is an convergent series. So we'll see one more example related to the Cauchy's root test. So test for the convergence of un is equal to n square by 2 power n. So here also we can observe that the function having the n powers of n. So we have to apply the Cauchy's root test only. So take the function un is equal to n square by 2 power n. Applying power 1 by n on both the sides, I will get un power 1 by n is equal to n square by 2 power n whole power 1 by n. On simplifying the equation, I will get n power 2 by n divided by 2 power n whole power 1 by n gets cancelled. I will get only 2. I can take the constant 1 by 2 outside. I will write the equation n power 2 by n like n power 1 by n whole square. I can write it. So after rewriting the equation, I am going to apply the limit n tends to infinity on both sides of the equation. So I got the equation like limit n tends to infinity un whole power 1 by n is equal to limit n tends to infinity n power 1 by n whole square divided by 2. And we know that limit n tends to infinity n power 1 by n will be equal to 1. So on replacing that formula here, the solution will be 1 by 2. 1 by 2 is obviously less than 1. So hence by Cauchy's root test, summation un is an convergent. So the next example is Test the convergence of summation n from 1 to infinity n plus 1 whole power n into x power n divided by n power n plus 1. So here also the function is expressed in terms of powers of n. So we have to use the Cauchy's root test. So let me take the function un is equal to n plus 1 whole power n x power n divided by n power n plus 1. I can rewrite the equation like this. By taking power of 1 by n on both sides of the equation, I will get the equation like un power 1 by n is equal to n plus 1. On applying the power here, the n gets cancelled in the numerator, so I will get n plus 1 into x. In the denominator, if I applying whole power n plus whole power 1 by n, I will get the equation like n power 1 plus 1 by n. So on simplifying the denominator, I can write the equation like n into n power 1 by n. I can write it. The equation will be now n plus 1 by n into x by n power 1 by n. So in the numerator, I can take one n common factor, or on dividing the equation, I will get the equation like 1 plus 1 by n. I can write it into x by n power 1 by n. So now to satisfy the Cauchy's root test, I am going to apply the limit n tends to infinity on both sides of the equation. So the equation will be limit n tends to infinity un power 1 by n is equal to limit n tends to infinity 1 plus 1 by n divided by n power 1 by n into x. So as we know that, so if I apply the limit in the numerator, so 1 by infinity will be 0, I'll get only 1 plus 0 there, divided by, in the denominator, if I apply the limit from the standard formula, limit n tends to infinity, n power 1 by n will be 1. So I can replace that complete value is 1. So I can keep the value of x as it is. So now we'll fall on to three cases. So how to test the convergence here? So by Cauchy's root test, we have summation un will be convergent when means if x is less than 1. Summation un will be divergent if x is greater than 1. And this a test going to fail if the value of x will be equal to 1. So in the next lecture, I am going to discuss about few more examples on D'Alembert's ratio test. So if you got any doubt while solving the problems, please leave a comment in the inbox so that I can respond for the same. Thank you.